with the slit, right? And let's do rectangular because that's easier for you to draw. We'll talk about circular next. With the slit, if it's not too small, right? And I have a wave coming in. I don't care if it's light. I don't care if it's sound. Any wave whatsoever comes in. What's going to happen whenever it goes to the slit? Yeah, the slit becomes like a brand new point source, right? And it starts to spread back out. And so, if this is true, what we're used to, right? A screen over here. If I were to draw an intensity pattern on it, I just see, it's very intense here, and then it gradually curves off, right? It gradually curves off, but the entire region is lit up. The farther the side you get, the weaker it is, right? But there's still light there, so the light's spread back out. It's just the entire strip gets lit up. Does that make sense? Now, whenever you make the slit small enough, you get an interference pattern. What I mean by that is I have monochromatic coherent light coming in, and we're going to make the single slit very small. Over here on the screen, a pattern shows up like this. Now let me get where the center is going to be. A very intense central maximum, and by the way, the central maximum should be even here. A very intense central maximum point. That means right there in the center you get a very, very big bright spot. Okay? But then after that, you have a minimum. Then it goes back into a maximum that is not as strong as the central maximum, minima, and so on, dying off with each one. What happens on one side is going to happen on the other. Okay? Not drawing the scale here, quite opposite. Central maximums are going to be caused by, now, I've been saying the word interference. The maxima, central and the elements, are going to be caused by what interference? Constructive. And the dark spots, the minimus, destructive. Okay? That's what's going to happen here. Let's go to why. I didn't talk about previously path difference leading to phase difference. I haven't talked about path difference leading to phase difference yet, so that's where I'm going to get. Yes?
Deconstructive or what?
Deconstructive to undo the construction, not that I know of. Yeah. Now, two waves come in, like here, that are coherent. Coherent means in phase. Right? So in other words, I have two waves. Let's say they're sine graphs. They look like this. And so initially, they're nice and together. They're giving constructive interference, right? Now, what if I take the bottom wave and I make it travel half a wavelength further? I take the bottom wave and I make it travel half a wavelength further. In other words, there is a path difference. One has to go a farther path than the other. Okay? Path difference. I take this guy and I'm going to, now he still starts right here, right? Top guy. But this guy has to go half a wavelength further, right? And I'm not sure I have this perfectly lined up, but if I make him go half a wavelength further, slide him back 1/2 wavelength, what type of interference occurs? Yes, destructive. Good. You see that? The crest and the trough is now matched up. The trough and the other crest is now matched up. Right? This would be a path difference of 1/2 lambda. Path difference of 1/2 lambda. Okay? 1/2 lambda leads to a phase difference, right? Phase being where it's at the position of the wave, leads to a phase difference of, I mean, check this out. If I were to kind of extend this guy down, of pi out of phase, 180 degrees out of phase. One went up, the other went down, causing destructive interference. This is path difference leading to a phase difference, thus here, destructive interference. Does that make sense to everybody? Okay, a lot of points. Yeah?
What exactly does it mean to make it have to travel an extra halfway?
I'm glad you asked. Now, back here. At this spot right here, and I'm going to, at this spot right here, some of the light has to travel further than other light. Some of the light has to travel further than other light. Here's what I mean by that. Let's take the top light that hits the top of the slit. Right, and let's call this distance it travels L. Just giving it a variable. Okay? And let's take the light also from that hits the center of the slit, and that's kind of the average for what's going on everywhere else. Okay? Light that hits the center of the slit. Which one of those lengths that I just drew, the green and black, is longer? Black, right? It starts from lower, and so if you wanted me to, right, I could draw triangles here. I'll do that in the race. Draw triangles here, right? Which hypotenuse is going to be longer, the green hypotenuse or the black hypotenuse? It's black, right? Because it has a higher height over on the other side, right? It has a taller height over on the other side, meaning whenever you do Pythagorean theorem, a squared, b squared, c squared, or c squared, if the other side, the opposite, let's say it's A, is bigger on the black triangle, that means its hypotenuse, C, has to be longer. Does that make sense? That means what's happening right here. Let's get rid of triangles. That means what's happening right here is there is a path difference. There is a path difference. Okay? But path differences lead to phase differences.
Well, you expressed it in graphs. Well, can you remind us of that?
Sure.
What are the axes? What is
Axes here. This is going to be distance, right? And then the y-axis we can label whatever we like here. For light, this would be intensity. The intensity of light.
So that would mean that the graph on the bottom is the light on the middle of the slit, right?
Correct. Correct.
But why you express it as starting earlier on the distance scale instead of starting at the same point and simply going farther, which would create
let's go about it the actual way that's happening. I just need to show here, these two graphs, that if something goes half a wavelength further, right, then there's destructive interference. Now, how this actually is looking, they're starting at the same point, right? They're starting at the same point, and this is always tough to draw, but I'm going to try to draw it here. One is going straight across for all practical purposes here. It doesn't have to, but for what I'm going to draw, it's going to go straight across. So this wave is up, down, and let's say it finishes where on the spot right here, and a down. Okay. The next wave doesn't get the luxury of going straight across. It actually has to travel a longer length, right? It has to travel a longer length. That means its starting point. I'm going to have to draw two pictures to try to show what I'm talking about here. Its stopping point, if you will, is farther away, right? So I'm going to keep this flat here just for the sake of argument, but just for the sake of being able to picture it. That means that it has to go farther. I need to draw a longer line for it to get it, right? Its stopping point, which is technically at the same point here, okay, is farther away. And so this wave, it starts out coherent, but ends up being out of phase. If I'm going to try to draw this with more angles in it, where maybe you can see what's going on here, and this is always fun to draw, right? I got a little slit. Here's the axis going across to the screen, like from this one, you know, up, down, up, down, up, down, up, and let's say it finishes on the up. From the middle, it's going to do the same thing, up, down, but it's gradually, slowly getting out of phase here, and it should finish on the, and I'm having trouble drawing, quite honestly. It has to finish on the down. That's what causes the dark spot. That's what causes the dark spot there. Okay? Destructive interference occurring. Coming all the way back to my first slide here. For destructive interference to happen, you must have a path difference of 1/2 lambda, or intervals of 1/2 lambda. And
What causes like two waves to be and destruct each other? Because there could be, I always thought of it as two parallel waves, and they just happen. I never thought about why they're. Is it based on which one you pick up in your statistics?
No, it's the principle of superposition. It's the principle of superposition. When two waves occupy the same region of space at the exact same time, they just simply add up. They just simply add up.
They weren't the same space.
Right? Here, these two waves from this one, the two waves, the wave that's going along the length, green L, and then the one along the black. Okay, I'm going to get to labeling that here in a second. They occupy the same space at the same time at one point, over at the red dot there, from how I have it drawn. Okay? Those two rays occupy the same space at the same time at one point, over at the red dot, where they meet, right? And so at that point, and just that point, they are going to interfere. The principle of superposition is going to occur. They're going to add, and if they're both on the up, if you will, they're going to constructively interfere. If they're both on the down, they're going to destructively interfere. If they're both on the in-between, then you're going to get something between constructive and destructive, right? Depending on where they're at.
All that matters is what part of the wave they're on at the point they touch.
Yes. Yes. Now, destructive interference means they're pi out of phase, which means you have a path difference of 1/2 lambda, meaning this length right here has to be L plus 1/2 lambda. Does that make sense? Yes, no? Yes, okay. Now, this is where drawing gets a little tricky here. I'm going to come down here and let me redraw, kind of blowing it up, making the slit a lot bigger. I have one going like this, that was length L. I had one starting here from the center, going up, this was L plus 1/2 lambda, going up there and intersecting on the string, causing destructive interference. Now, let me label this entire piece, the entire slit width, B. Let me label the entire slit width B. Okay? Let me try to draw in a right triangle where there is my 90 degrees. So this is B over 2. The hypotenuse of that triangle would be over 2. Everyone see that? Label this theta. Label that theta, if you will. Okay? this part of the triangle right here, this base right here, is the path difference. That's how much further he went. In other words, this piece, this entire thing, it's not even looking back. This entire length is L plus 1/2 lambda. So that piece is going to be 1/2 lambda, and this piece over there is going to be L. Okay? Are you okay with this? So deriving around the basic equation that you're going to end up using in all these problems. Okay, you just have to see the derivation because you have to be able to explain path difference basically. Okay. Now, sine is what? Sine theta equals. Good, so sine of theta is going to equal 1/2 lambda divided by 1/2 b. You okay with that, Paul? Right there? Hypotenuse is the b over 2 part. Hypotenuse is the b over 2 part. What happens to the 1/2s? They go away. So now I got sine theta equals lambda over b. Now I'm not done with this derivation. I'm about to do something called the small angle approximation. If you think about the demo that I just did, the laser and everything else here, the distance, Scott, can you give me an approximate distance between that central bright spot and that first dark spot on that wall? Just, you know, it's not there now. Try to imagine it was there. About, give me an approximate distance.
So don't put
To the central bright spot.
I would say,
Yeah, a couple of centimeters, like 2 centimeters, right? Okay. And about how far is it from the laser over here to the wall? I'm thinking like, you know, dos, tres, cuatro. I'm thinking like 7 or 8. You know, almost 10 meters from there to there, right? 10 meter length, right? Yeah, well, yeah. Trying to make it a little bit easier. You know, 8, 10 meters somewhere in there length, and then a height of 2 centimeters. What angle are we dealing with here for a laser that's being swept out? If you're straight on, right, and it's being swept out a little bit to the right. That's a tangent, right? That's a tangent. Tangent of 2 centimeters divided by 10 meters. This angle is insanely small. Does that make sense? The angle is insanely small. Take out your calculators. Everyone test. Change it to radians, please. This only works in radians. Change it to radians. I want you to type in the sine, now in radians here, the sine of 0.01. What do you get? 0.09999 means 0.01, right? You get 0.01. Sine of 0.0, let's do 0.05. Increase it a little bit. What do you get? 0.04999, 0.05, right? 0.05. Let's go up a little bit more. Sine of 0.1. 0.1, right? Sine of should be sine of 0.1 should be about 0.1. Should be about 0.1. Double check the calculator. I'll come look at it here. Next, let's go up a little bit more. Sine of 0.5. 0.48. All right, now we're starting to diverge a little bit. All right, we're starting to diverge. Go all the way up to sine of 1.
Dougher at the office, Michaela Taylor. Here, call your family.
0.84. We have officially diverged. Right? We have officially diverged. Under small angles, sine theta is approximately theta. Under small angles, sine theta is approximately theta. That's the small angle assumption, and it can only be done in radians. And really, we're only going to do it with single slit fractions. With a single slit diffraction, the odds for angles being large are very slim. Whenever we get to diffraction gratings, the angles are going to get a lot larger, and we're not going to make this assumption. Meaning that theta here is equal to lambda over b. Make a small angle approximation, right? Assume this is a small angle. Sine theta is just theta. Sine theta is just theta. Let me give you another small angle approximation that you're going to end up needing here in a little bit. Tangent theta under small angles is also approximately theta. That's another small angle approximation of radius.
Why do you even need to approximate sine theta? Because you can use sine.
Brittany Stewart, please come down.
Personally,
Brittany
if this
Stewart.
was only me doing it, then I would just use sine. I wouldn't worry about it. But if they like, IB likes the small angle approximations. We'll run with it. All right. So now this is the equation that you find in your packet that you're going to want to use. But whenever it comes to usefulness of this, it's really not useful at all. I mean, let's come up here and let's look at what triangle we're talking about. Theta equals the wavelength of light divided by the distance between the slit. Not very useful at all. This angle doesn't matter at all, really. You know, it's just an angle. Let's get to an angle that does matter. Let's get to an angle that does matter, and this picture is about to get somewhat cluttered. Let me draw just a perpendicular line. Just a perpendicular line to a screen. Okay? Perpendicular line to a screen. Okay? Now, let's try to figure out what that angle is going to be. Try to figure out what that angle is going to be. Now, here's how I'm going to do this. What is that angle right there? 90 minus theta. Does everyone see that? Triangle has 180 degrees in it. One of those angles is 90 degrees, making that little angle in green that I drew right here 90 minus theta, if we're dealing with degrees here. Okay? If that's 90 minus theta, what is that? Which is going to be, this is theta, right? This is theta, right there. Another right angle, right? Another right angle between those guys. One half of it is 90 minus theta, leaving the other half of it just to be theta. That's where this angle comes and actually gets some meaning to it. So, what I can do here, let's set up a problem. What I can do here, I have a single slit with a width of, I don't know, let's say 35 micrometers. The width of 35 micrometers. And I shine monochromatic coherent light through it onto a screen, and I get a diffraction pattern that looks something, I get high intensity, minima, so on down like this. I take a ruler, right? Just a standard ruler or meter stick, and I know the distance between the screen and the slit is, let's say, 1.5 meters. With this small slit, I'm going to actually get some pretty good resolution, meaning things are spread out. And I know the distance to the first minima is, let's say, 15 centimeters. This is going to allow me to solve fairly accurately, very accurately, just taking measurements with meter sticks for the wavelength of light. Well, here's theta, as we just discussed. Forget that little in-between triangle, right? That was just part of the theorem. That was just part of the proof. Okay? There's theta. Now, Our base equation is theta equals lambda over b. I'm looking for lambda. I know what b is. I don't know what theta is. How can I get theta? That's sine. Yeah, good. I'm going to use tangent here, right? Tangent, theta is your opposite over your adjacent. In fact, in this entire unit, those two equations right there are going to be the two that you're going to use pretty much always practice. Those two equations right there are going to be the two that you're going to use for almost always practice. Okay. So now, tan inverse theta is going to equal the tan inverse, you need to do this in radians by the way, of the opposite, which, the opposite's what? Which is, in base units, 0.15 meters, divided by 1.5. What's theta come out to be in radians, please? 0.99. Now, the small angle approximation starts to break down what I just did, but 0.099. Okay, that's better. We're well within small angle approximation. Because we're making the small angle approximation. Since we're using this equation right here. Yeah. Since I'm making this small angle approximation, I have no choice. I must use radians. So now I can take this, plug it over here, 0.099 equals lambda over b, 35 micrometers. What does micro mean? 6. This is 35 times 10 to the negative 6. What does lambda come out to be? What is it? 0.00. Give me that in scientific notation, please. 3.5 times 10 to the negative. Negative 6 meters. Is that visible? No, that's a little bit longer than visible light. Visible light is around times 10 to the negative 7. Okay, times 10 to the negative 7. So you're able to solve the wavelength of light. The cool part about this, and it's going to get better with diffraction, at all. The cool part about this is the only measurements that I do are to take a meter stick and to measure the length from the single slit over to the screen, right? And then take that same meter stick and measure the distance between a central maxima and a minimum, right? The first minimum. That's all I have to do. Know the slit width, which whenever these are machined for you, they tell you what they are. From that, you're able to accurately calculate the wavelength of light down to a precision and down on scale. There's no way you could measure with any meter stick there, right? I'm just thinking negative 6. See what I'm saying here? All right.